Hello there. This video is all about the algebra of limits and the squeeze theorem. Now, up until now, we've investigated limits and talked about them involving graphs and tables. And we're going to take a look now and see if any algebra techniques are going to be able to help us to evaluate limits. Now, we're going to make this a little bit formal, but if you take a more advanced real analysis course, you'll see what are called delta epsilon proofs, which will make this a really formal process. But for right now, yes, you're going to have to show your work and explain your work, but these techniques will not be as formal as you might expect later on, because this is just kind of a survey course of calculus anyway. Let's talk a little bit about what we're going to do. Yes, there are quite a few examples here that we'll go through, but they're relatively quick. And I'm going to show you all these various techniques that we'll have, including what we call the squeeze theorem, to help us to evaluate limits. So a quick introduction. The focus of this particular PowerPoint is on how to use algebra to evaluate limits of indeterminate form. For our purposes right now, that's a limit of the form 0 over 0. And we'll see later types of indeterminate form down the road. Okay. I will tell you this, though. You should always try plugging in your limit value, your x value first, before you go on and try to do anything else. So if you're dealing with polynomials or rational functions where the denominator is not 0, exponentials or other functions that have no breaks, what we'll later on call continuous functions, the limit is just the function value. So I give you an example right here. The limit as x goes to 1 of x squared plus 1 over x plus 2. When we plug in x equal to 1 initially, we're going to get 1 squared plus 1, which is 2 in our numerator, and 1 plus 2, which is 3 in our denominator. So we get 2/3. There's no need for any of those techniques if we already know that our function is continuous at that point, because the limit is going to equal the function value. All right. So technique number 1 is going to be all about trying to find limits using factoring and other techniques. Right, and we'll see an example of that in just a second. So here we got limit as t goes to 2 of t cubed plus 3t squared minus 12t plus 4 over t cubed minus 4t. So the idea is if we get a situation where our numerator and denominator are both equal to 0, what we're going to call indeterminate form, we're going to try factoring and canceling. And synthetic division is going to be our friend in a lot of cases with this. Note, by the way, based on what I just said, you should try plugging in the limit x value, or t value in this case, first before you go forward. So here, when I plug in 2 into my numerator, I get 2 cubed plus 3 times 2 squared minus 12 times 2 plus 4, and I get 0 in my numerator. And I plug in 2 in my denominator, and I get 0 as well. So we have 0 over 0, which is what we call indeterminate form. It's not that we can't ever determine what the limit value is, it's just that we need another technique to figure it out. So what I introduced right here is this idea of synthetic division. The idea is if t equal to 2 is going to give us a problem in our numerator and denominator, it's probably a factor of our numerator and denominator. So what I need to do is figure out whether t minus 2 factors out of my numerator and my denominator. Now, we had a great technique for doing that back in algebra, and that was synthetic division. So here what I do is I put 2 in the box, and I put all of my coefficients up here on the top line. I won't go through all the details of synthetic division, but basically the idea is I should get a 0 right here if 2 is a 0 for my cubic on the numerator, and I will get what I call my depressed polynomial. And what this tells me is my numerator factors into t squared plus 5t minus 2, those are the coefficients right here, times t minus 2. I can also factor my denominator into t times t squared minus 4, or t times t minus 2 times t plus 2. So I used factoring to figure out that t minus 2 is a factor of my numerator and my denominator. That's what's causing my problem here. So because our limit has to do with what's going on around the value t is equal to 2, all right, I can reduce this down by taking out my factors t minus 2 in my numerator and my denominator. So I'm left with limit as t goes to 2 of t squared plus 5t minus 2 over t times t plus 2. The t minus 2's go away. All right. Notice, by the way, also that I'm leaving my limit signs. You leave your limit signs if you're just manipulating algebraically until you get to the point where you're actually going to plug in t equal to 2. So we're going to try it again after we factored and canceled. So now when I plug in 2 into my numerator, I get 12, and 2 into my denominator, I get 8. And so I get my overall limit value to be 3 over 2. right, so find limit as x goes to -4 from the right of 1 over x squared minus 16. So your knowledge of a function or investigating nearby values can help as well. One thing that I will do first is I'm going to factor my denominator. So I'm going to say the limit as x goes to -4 from the right, remember that symbol, of 1 over x minus 4 times x plus 4. Right? And one of the things that you'll notice when we go about taking a look at this is if I were to plug in -4 into my denominator, I get a -8 with my first factor, and then I'm plugging in a number that's close to -4, but a little bit above -4. So something like -3.9 or -3.99. What happens when we plug that into the factor x plus 4 is we're going to get a number that's very, very close to 0, but is a little bit positive, right? Because -3.9 is a little bit above 4. So I'm going to write that with kind of some sketchy math notation. This isn't really math notation, but it's kind of like our scratch work. And we're saying we get a number that's a little bit above 0, or maybe what we might call positive 0. The idea is, what does this function approach just to the right of -4 on the number line, such as -3.99? Well, when we have a non-zero number in our numerator, like 1, and a number close to 0 in our denominator, the limit is going to approach either positive or negative infinity. And the reason why is because we're taking a number like 1 and dividing by a number that's really, really close to 0. And so we end up with a number that grows without bound, either negative infinity or positive infinity. So what we get, positive or negative infinity, will depend on the signs of our numerator and our denominator. In this case, we have a positive number in our numerator and a negative number and a number that's positive close to 0 in our denominator. So we have one negative altogether, so we would say our limit is equal to negative infinity. Technique number 3, all right, we can use piecewise functions to find limits as well. So for example, we've got this piecewise function that's composed of a linear function, a quadratic function, and another linear function. One of the things that we'll learn later on is that these functions are both what we call continuous. They're not mysterious functions, right? And they're functions where our limit value is equal to our function value. So in order to evaluate something like this, all we have to do is plug in our x value into the right piece of our function. So for example, limit as x goes to 0 from the left of f of x, we'll need to figure out which piece has to do with x with a little bit less than 0 values. So that piece is actually our top piece. So numbers like -0.001, those will all get plugged into our top piece, which is the 4 plus 2x portion. And since this is not a mysterious function, it's a linear function, all we've got to do is plug in 0 into our function, and we get 4 plus 2 times 0, which is 4. So the left side limit, the left side portion to the left of 0, gives us a limit of 4. If I wanted, on the other hand, to find the limit as x goes to 0 from the right of f of x, I need to consider values that are a little bit bigger than 0, so like 0.01. Well, those values fit in to the middle portion, numbers that are a little bit bigger than 0. So I plug into the -5x squared portion. When I do so, I get a value of 0. So the right side limit is 0. The left side limit was 4, so we would say the overall limit, limit as x goes to 0 of f of x, does not exist, or DNE, because the left side limit doesn't match the right side limit. You got 4 on one side and 0 on the other side. So for piecewise functions, all you got to do is investigate what's happening on the left and the right side pieces. All right, finally, our last technique here. And limit as x goes to 4 of the square root of x minus 2 over x minus 4. Again, the very first thing you should always do is to try to plug in 4 first to see what happens. In this case, we get the square root of 4 minus 2 in our numerator, right? That gives us 0 overall. And we get a 4 minus 4 in our denominator, which also gives us 0. So the technique that we're going to use here is going to be called rationalizing, and we're going to rationalize by multiplying and dividing by a conjugate. Now, your algebra brain might make you think like, this is crazy. What are you doing here? What we're going to do is we're going to end up getting a square root in our denominator. Usually we rationalize to try to get the square root out of our denominator. But here the key is we want to get rid of our factor x minus 4, which is causing us to have the divide by 0 error. So what we do is we multiply and divide by the conjugate of square root of x minus 2, which is the square root of x plus 2. And we're going to multiply and divide by that factor. When you do that, we're going to end up with a square root of x minus 2 times the square root of x plus 2. That ends up being x minus 4. In our denominator, we're going to leave this alone as this product right here as x minus 4 times the square root of x plus 2. And we notice, just like with the factoring techniques, we're going to be able to reduce this down because we have a factor of x minus 4 in our numerator and denominator. So again, we're keeping our limit signs as we're manipulating with algebra here. And we get the limit as x goes to 4 of 1 over square root of x plus 2. Once we've gotten rid of our x minus 4 factor, we plug in 4, and we end up with a 1/4. All right, so this technique allows us to get rid of what was causing us to have a 0 over 0 indeterminate form to begin with. One last technique we're going to talk about is what we call the squeeze theorem, or the sandwich theorem, or the pinching theorem. All right, and all these various names get at one big idea right here. So in my graph, I've got this function y equals x squared times cosine of 1 over x. That's the red graph right here. And what's happening is this function fits nicely in between the blue graph of y equals x squared and the green graph of y equals negative x squared. And as you can see, if I want to figure out what the limit of the red graph is as x goes to 0, right, it's being squeezed in by these two functions, blue and green, which are both going to y is equal to 0 as x goes to 0. So what we'll say is if f of x is less than or equal to g of x, which is less than or equal to h of x, in this case the g of x function is the middle function, our red function, when x is near a, except maybe at a. And we know that our blue and our green functions, f and h, are both approaching the same limit. In other words, limit as x goes to a of f of x equals limit as x goes to a of h of x, and they both equal the same limit L. We know the red function, the limit as x goes to a of g of x, has to also be L. We're forcing our function into a nice little sandwich right here. The red is like the nice little piece of cheese in between two pieces of bread. Ew, blue and green bread, I don't think that's going to work, but whatever, you get the idea, right? We're squeezing our function in between two functions that we know the limits for. How can we use this? Let's say we want to find the limit as x goes to 0 of x times sine of 1 over x. That's the red graph right here. And we can see in our picture right here that it fits nicely in between the green functions y equals negative x and the blue function y equals x. Oh, for example, our process might look something like this. We know that every sine function, including sine of 1 over x, has to be between negative 1 and 1 as its range values. What that means, if I multiply everything by x, negative x has to be less than or equal to x times sine of 1 over x, which is less than or equal to x. Right, so it squeezes right in between those two functions. However, we know the limit as x goes to 0 of negative x and the limit as x goes to 0 of positive x both equal to 0. Those are nice, easy functions to deal with. Well, what that means is by the squeeze theorem, the limit as x goes to 0 of x times sine of 1 over x also has to be 0 because that function is squeezed nicely right in between our two linear functions there. So we proved it without even having to factor or anything. What a nice theorem. The squeeze theorem also allows us to prove some nice, easy limits, like the limit as x goes to 0 of sine of x over x. And we can see by this graph that we're squeezed in by two functions to make that limit equal to 1. We'll show this in class, but basically the idea is that sine of x over x is squeezed nicely in between cosine of x and 1 over cosine of x, which we knew to be the secant of x function. We'll show that later on. But what we're going to be able to say is the limit as x goes to 0 of cosine of x is equal to 1, and the limit as x goes to 0 of 1 over cosine of x is also equal to 1. Well, because cosine of 0 is 1. Right? And so by the squeeze theorem, we'll be able to show that limit as x goes to 0 of sine of x over x is equal to 1. This will be a really important limit going forward when we try to prove trig derivatives. We'll also be able to show later on that limit as x goes to 0 of 1 minus cosine of x over x is also equal to 0. So hold on to those thoughts for now. In summary, we have so many techniques to evaluate limits that are in what we call indeterminate form, many reminders of our great days in algebra and pre-calculus, factoring and canceling and rationalizing and all those things. We also have the use of what's called the squeeze theorem, which will be a great theorem if we know a little bit about the behavior of the function and how it relates to other functions and their limits. Thank you for listening. We'll see you on the next video.